Now let us take some other examples of dynamical systems and check whether there are periodic orbits or not. So consider this example. So in which x1 dot equal to x2 plus x1 times x2 square, x2 dot is equal to minus x2 plus x2 times x1 square. So we differentiate the first. In order to use Bendixson criteria, this particular quantity that we were to evaluate is nothing but divergence of f. Yeah, divergence of f is also denoted as dot product of this operator with f. So when we evaluate this, we get x2 square here, and so there is something wrong here. This x2 should have been x1. So please note that there is a small mistake here. If we have x1 here, then we get this. So now we have that this is always positive. Yeah, after you substitute x1 here, you get that this is always positive. So if the Lotka this is very similar to the Lotka-Volterra Predator-prey model. After we have x1 here, this is very similar to the Lotka-Volterra Predator-prey model. If it had depended on not just the product of x1 x2, but some higher order power of one of the species, then it is possible to show that the Bendixson criteria says that there are no periodic orbits. Why? Because the divergence of f is always positive except at the equilibrium point. So hence by Bendixson criteria there are no periodic orbits. Now consider this example. This example also has, we should have a modification here. We should have x1 here in place of, in the second equation, x2 dot equal to minus x2 times x1 square. So here we see that this changes sign. This only means that inside the region where it has the same sign, there is no periodic orbit contained inside that region. This is an example that we have already seen. Now we will study an important case where we have an epsilon here along the diagonal entries. Yeah. So for this particular A, in which we have epsilon along the diagonal, what can we say about the equilibrium point? So when epsilon is greater than 0, then the equilibrium point 0, 0 is unstable focus. This is something that we have already seen. What happens when epsilon is less than 0? When epsilon is less than 0, the eigenvalues of this matrix are epsilon plus minus 2j. So epsilon greater than 0 implies unstable. Unstable node or focus, it's unstable focus because the imaginary part is non-zero. And for epsilon less than 0, we have a stable focus. So this is what we will say, that as a, if this epsilon, this is our epsilon value, and this is, let's say, radius, distance of the point from the origin. So if epsilon is some positive quantity, the epsilon itself is not dependent on x1, x2. Yeah? So it is just the same positive number. Positive means unstable focus, and if it is some same fixed negative number, then it is stable. So this is unstable and this is a stable focus. So how about modifying this epsilon as a function of radius so that we have trajectories that converge to a periodic orbit? So this is what we will see in detail. So what if epsilon changes its sign, depends on the distance from the origin and changes its sign? So consider this differential equation in which along the diagonal we have put 25 minus x1 square minus x2 square along the diagonal, and the off diagonal term we keep constant, doesn't depend with change with radius. So this is nothing but writing it in this form, in which along the diagonal we have some function that depends on the radius, depends on the distance from the origin. Now we consider the case when r is equal to 5. For that case we have this epsilon of r is equal to 0. We can consider the case when r is less than 5. For r less than 5, the diagonal entries are positive, and when r is greater than 5, the diagonal entries are negative, are both negative. We cannot speak of eigenvalues of this, the eigenvalues of this matrix itself depends on x1 and x2. we speak of eigenvalues of only constant matrices. So it appears like if we make this radius, if we make this diagonal entry depend on radius, then we will have trajectories either coming towards origin or going away from the origin, depending on whether we are inside a particular circle, whether we are inside the circle of radius 5 or outside, and on the circle itself we are going to be remaining on the circle. So let us check. This is a circle of radius 5. So when x1 is equal to 0, so this is radius 5 circle. Okay. So when x1 is equal to 0 and x2 is equal to 5, the time x1 dot, so x1 equal to 0, sorry, the orientations, we start again. How do we get this orientation? We expect that for radius equal to 5, we have a periodic orbit. Why is it that we have a periodic orbit? You put r equal to 5 and you see that the matrix A, it looks just as if, so check that x1 of t, x2 of t equal to 5 times, so along a circle x1 x2 are like cos and sine of a function of what frequency? T, of just cos t and sine t. Why? Because omega is equal to 1. For this particular A, the solutions are x1 x2 are equal to cos and sine to the sine of the quantities and of radius 5. And why cos t sin t? In general it would have been cos omega t sin omega t, and then omega is equal to 1 because of diagonal entries are equal to 1. Now we are going to decide why is it clockwise and not anti-clockwise. That we can check by taking some sample points. So consider this point. This is x1 component equal to 0 and x2 equal to 5. So consider the point 0, 5. At 0, 5, when this acts on 0, 5, when A acts on this matrix, then we get that this is equal to 5, 0. So the x1 component is increasing at this particular point. That is why it is along this direction. Yeah. So by using the same argument, we can decide where cos of t should come, where sin of t should come, and whether there should be a negative sign to one of these. Now the focus of this particular topic is to see what happens for radius larger than 5. For radius larger than 5 and for radius smaller than 5. So for radius larger than 5, there is the off diagonal terms indeed cause some rotation, but the diagonal entries cause a decrease in the radius. That is why it is coming inwards. Yeah. So we have these arrows coming inwards, and for the circles inside the circle of radius 5, that is for circles of radius less than 5, there is some rotation caused because of the off diagonal terms, but the diagonal entries themselves are positive, which is causing this radius to grow as a function of time. This is an important property that we will exploit to say that all initial conditions except the equilibrium point 0, 0 are all converging to this special periodic orbit. Which periodic orbit? The periodic orbit of radius equal to 5. So let us check. Let us use Poincare-Bendixson criteria and check that there indeed exists a periodic orbit. We are not able to say that this is a center kind of arguments because we can use that only for a linear system by linearizing at an equilibrium point. So take M to be equal to the set set of all x1 comma x2 such that x1 square plus x2 square lies in the interval 4 to 6, closed interval. So what is our set M? Let me write again. Set M is a set of all x1 comma x2 points such that x1 square plus x2 square is less than or equal to 6 and x1 square plus x2 square is greater than or equal to 4. In other words, this is a circle, supposed to be a circle. This is another circle. This is a circle of radius 4. This is a circle of radius 6. All the points in this ring, these are all the points whose distance from the origin is greater than or equal to 4 and less than or equal to 6 also. Yeah, this and this. So we will now check that this particular set M is positively invariant and has no equilibrium points inside it, and it's compact. The compactness is satisfied because it's a compact set and it's a closed set, because these inequalities are non-strict inequalities. They're not strict equalities but non-strict inequalities. Because of that fact, this is a closed set and it is a bounded set, because we see that all the points are at most distance 6 away from the origin. Hence it's a bounded set. So in order to use Poincare-Bendixson criteria, we are going to check that this set M is a positively invariant set also. So when would Poincare-Bendixson criteria be applicable? The set M should be a closed and bounded set, should be positively invariant, and there should be no equilibrium point inside it, or at most one equilibrium point, which is either an unstable node or an unstable focus. So let us check what is the property of this particular M. We show that M is positively invariant. So how can we show that this set M is positively invariant? So what we will do is, we will take the circle of radius 6 and we will check that this circle of radius 6, the outward, the vector that is perpendicular to this boundary is outward like this. This is a vector. We will check what is the inner product of this vector with the vector field. If at every point along the boundary this vector field is directed inwards, it means that all the points or trajectories are coming inwards. Yeah. What are these vectors? This is a unit vector perpendicular to the boundary and directed outside the region. The region is directed, the region is inside this. As far as the boundary 6 is concerned, as far as this boundary of radius 6, circle of radius 6 is concerned, this is a vector that is directed outwards. So let us check whether, what is this vector? It is nothing but x1, x2 vector. Its inner product with f of x at that point. F of x at each point is again a vector of dimension 2. We will check whether this inner product is positive or negative. If this inner product is negative on circle of radius 6, it means that along this circle all trajectories are going inwards. Why is it inwards? Because this is a vector outward and this is the f of x. If this particular angle is, this dot product being negative, means that the angle between the two vectors is an obtuse angle. Why? Because what is the dot product of w dot product with v? This is equal to w norm times v norm times cos of the angle between w and v. So if this quantity is negative, it means these two quantities can't be negative. So this cos theta is negative, and cos theta is negative only for theta beyond 90 degrees, which means that this angle between these two vectors is greater than 90 degrees. And since this vector is a vector that is directed outside the boundary, this angle being obtuse means the f is directed inwards. So let us check whether this quantity is negative. So x1, x2 times f of x. So f of x is what we can see from this particular thing. f1 of x is first row times x1 x2. So this is nothing but x1 times 25 minus x1 square minus x2 square plus x2. This is f1 of x, and f2 of x is minus x1 plus x2 times 25 minus x1 square minus x2 square. So when we do the dot product of this, that is nothing but this row vector times this column vector. When we evaluate this, let us see what we get. So x1 square times 25 minus x1 square minus x2 square plus x1 x2. This is just this quantity here that I have written is just x1 times the first component here plus x2 times minus x1 plus x2 square times 25 minus x1 square minus x2 square. So x1 x2 minus x1 x2, these both cancel. So we get x1 square plus x2 square in common, 25 minus x1 square minus x2 square. Now we are going to note that we are going to evaluate this along the circle of radius 6. So we get 6 square times 25 minus 36. Yeah, so this is some quantity that is less than 0. That is all we needed. So this proves that along the circle of radius 6, the arrow is directed inwards. Now let us check what happens along the inner circle. This is a circle of radius 4, yeah, and along this boundary, this is a unit normal, and the f itself. So there are two vectors at each point along the boundary. One vector is the direction of f of x at that point, and another vector is the direction of the unit normal, and in this case this vector says that it is directed inwards. Why? Because m lies to the outside of this region, outside of this circle. Yeah, m was the set of all points of radius greater than or equal to 4 and less than or equal to 6. Since we are taking a circle of radius 4, the region is to the inside. So this vector is directed inwards of the region. So at each point, what is this vector? It is just x1 x2 again, and the direction of f at that point is f1x f2 of x. Now because this vector is a vector directed towards inside the region along the boundary, this particular quantity being greater than 0 means that the angle is acute angle. The angle between the two vectors is less than 90 degrees, and then it would mean that the trajectories are all coming inwards into the region. Yeah, so there are all these trajectories that are coming into the region as far as the boundary is concerned. As far as which boundary is concerned? The circle of radius 4. So by the same argument, all we have to do is we have to now substitute x1 square plus x2 square is equal to 4 square and not 6 square, and this quantity becomes 4 square when we are looking at the circle of radius 4, and this quantity becomes 25 minus 16, which is now positive. So this is greater than 0 on circle of radius 4. So this proves that the set M is positively invariant. How have we shown that this set is positively invariant? We have said that this set M has boundary consisting of two circles. So this is one boundary of circle 4, the other boundary is circle of radius 6, and the region is like this. This is the region M. All along the outer circle, the trajectories are coming inwards into the region. This is what we checked because the angle was obtuse there. All along the inner boundary, also the trajectories are coming inwards. Yeah. So check that as long as the region M is defined as set of all points where the radius of the where x1 square plus x2 square is greater than or equal to say 4.9 and less than or equal to 5.1, it will still be positively invariant. That is the only property that we used. So such an M will be positively invariant and hence it will contain a periodic orbit. Is there an equilibrium point inside this region? That is another thing we are supposed to check before we use the Poincare-Bendixson criteria. This is the last thing we will check before today's lecture ends. So let us put f1 of x equal to 0 and f2 of x equal to 0. So f1 of x we had evaluated and we had got that equal to, so what is shown here is f1 of x and this is f2 of x. We have to substitute both equal to 0 and find the values of x1, x2 such that both these functions are equal to 0. Those x1, x2 values will comprise the equilibrium points. So one can check that the only equilibrium point for this is x1, x2 equal to 0, 0. In other words, if M is a set of all points of distance greater than or equal to 0, if the radius is strictly greater than 0, then M will not have any equilibrium points. That is why we can, so this implies that x1, x2 equal to 0, 0. x1, x2 equal to 0, 0 is the only equilibrium point. The equilibrium point itself is stable or unstable, one can check. Let this be as a homework that this equilibrium point is unstable. Why? Because at this equilibrium point we ensure that the diagonal entries of this particular matrix, of which matrix, let us go back to the slide, of this particular matrix for x1 equal to 0 and x2 equal to 0, this particular matrix has diagonal entries positive and hence the equilibrium point is an unstable focus. So this allows us to use Poincare-Bendixson criteria, since the region that we have considered, set of all points of radius greater than 4 and less than 6, greater than or equal to 4 and less than or equal to 6, is compact, is positively invariant and has no equilibrium points, and hence there is a periodic orbit. By making this set M smaller and smaller such that it just contains the circle of radius 5. So we can take the region of M to be set of all points of distance slightly less than 5 and slightly more than 5, and it will still, the same argument will hold and there will be a periodic orbit. This shows that there is no continuum of periodic orbits here, there is an isolated periodic orbit for this particular example. We will consider modifying this example and obtain the van der Pol oscillator as a special case.